We learned in the last section how to find the circumference of a circle, the distance around it. Now we're going to talk about the area. And this was something I didn't learn until I was an adult. If I ever was taught this in middle school or high school or even college, I just forgot. But I think this is pretty cool. So we talked about how Archimedes figured out the value of pi in order to determine the circumference of a circle. But then the question is, how could we use this information? How could we take the circumference and figure out the area of the circle? So they actually did it this way. So let's say you cut the circle, almost think of it like a pie, and you cut it into lots of different slices. So here they cut it into, I think, 16 slices. And they said, okay, we'll take the 8 slices on top and face them all with their points down. So this, and this. Those are the 8 slices from the top half that are facing down. Then they said, let's take the 8 slices from the bottom half and point them upwards. So here. Get the idea? So they fit these slices together in such a way that it forms something really close to a rectangle. Now, I won't go into detail, but there's a way they basically said, okay, it gets really close to being a rectangle, or a parallelogram is probably a better way of thinking me to say, a parallelogram, when we do like 16 pieces. But you imagine, what if we did 1,000 pieces, or 1,000,000 pieces, or even more? You can tell this is already pretty close to a parallelogram just with 16 pieces. So the more and more pieces we get, the closer this is to an actual rectangle. And they figured, okay, we took the top 8 slices, that's half the circumference of the circle, which half the circumference, that means that's the length or the base of the parallelogram. And then the radius, because that's the distance from the center of any of these slices to its edge. So the center to the edge gives us the radius. So the height of this parallelogram is the radius of the circle. So we've just taken a parallelogram, which we do know the formula for. You see it down here, a equals base times height. Now let's convert it to what we know about circles. So here's what I mean. We talked about the fact that when you arrange these pi pieces this way, the base is half the circumference. So we can replace the letter B, base, with half the circumference. And we know the height, as shown right here, is the radius. So we can replace the height with r. So when this is rearranged into a parallelogram, half the circumference is the base, which you see right here. The height is the radius, which you see right here. And they said, okay, this is good. So we've now converted this to be everything we can know from a circle based on just the circumference formula. But then, believe it or not, they're like, but we can make this even easier. We don't want to have too many different kinds of variables in here if we can help it. So they said, well, we know the formula for the circumference of a circle. One of them is 2 pi r. So we can substitute 2 pi r in for the c. So they replaced 1/2 c with 1/2 times 2 pi r. Because we know from the circumference formula that the circumference is equal to 2 pi r. So now there's blank spaces here, so we can simplify this together. Half of 2 is 1. So that just leaves pi r on the inside times r on the outside. And then r times r is r squared. So that's how they got the formula for the area of a circle. They basically figured out they could convert a circle into a parallelogram and use that formula to figure out the area of a circle. I think that's pretty cool. I know I'm a nerd because I'm a math teacher, but I think that's pretty amazing. They used something they already knew, a parallelogram, to figure out something they didn't know, the area of a circle. But that being said, if you didn't understand everything I just taught about how this got created, that's okay. I'm not going to ask you to bring that out again. But you do need to remember that this formula is the area of a circle. One thing you should note, there is just one formula for the area of a circle. They don't use a formula that has the diameter in it. So for the area of a circle, we just have one with the radius, pi r squared. So if a problem gives you the diameter instead of the radius, make sure you divide that radius, divide the diameter by 2 so you know the length of the radius and can plug it into this formula. And that'll make more sense once we get to it on the back. Okay, so number 1 is kind. They already gave us just the radius. We know the area is pi r squared. So I plug in 9. And if you want to square that first, you can. You can say pi times 81. Then you plug in your calculator. But I will show you how it doesn't matter if you square first or not. You can get the same answer either way. So if I plug this in and I say pi times 9 squared, gives me that answer. Or if say pi times 81, that also gives me the same answer. So either way is okay. You can just do the squared in the calculator or before. So again, this would be 2.54.47. Because while it says 46, we look at the number past the 6. That's a 9. That's bigger than 5. So we have to round the 6 up to a 7. So the answer is 254.47 square meters. And we do have to square the units because we're doing area. With area, it's always squared units. Okay, now number 2 does what we talked about at the bottom of the front of the page. They give us the diameter. We cannot plug that into this formula. There's no D in this formula. But we know the diameter is equal to 2 times the radius. So if the diameter is 15, we can divide both sides by 2 and figure out that the radius is 7.5 feet. So that is what we will plug in to our equation. So we get pi times 7.5 squared and we get 176.71. So 176.71 square feet. Okay, number 3, they gave us the radius, so we can just plug that in directly as it is. The radius is 11, so we do pi times 11 squared. And we get 380.13. So 380.13 square meters. Sorry, I didn't write that well. 380.13 square meters. Number 4, though, we get back to where, they give us the diameter. There is no diameter in the formula. There's only the radius. So we have to cut this in half. Because if the whole thing, the diameter is 8.2, then each individual piece, each half, is the radius. That's 4.1. So we would plug in 4.1 in for R. We get pi times 4.1 squared. 52.81. So 52.81 square inches. And just like we talked about in the circumference, sometimes they won't draw a circle for you. They'll just give you information, but you still do the same process. If they give you the radius in this case, you can just plug it in directly. Pi times 13.2 squared. You can type that in your calculator and you get 547.39 square kilometers. But if they give you the diameter, you've got to cut this in half. The radius is half this amount. So 4.8 divided by 2 is 2.4. So we do area equals pi times 2.4 squared, because we can only plug in the radius. We can never plug in the diameter into the area formula. And when I type pi times 2.4 squared into the calculator. I get 18.10 square miles. Okay, last example. The center part of the hockey rink, called the neutral zone, that's the circular part right here. Oh no, sorry, it's the whole thing. So the central part of the hockey rink, if I remember right, the hockey rink is like this, is long this way, like this is half. Then there'd be something past this paper over here. Anyway, so the central part of a hockey rink, called the neutral zone, is a rectangle, which you see here, with a center circle as shown below. So what is the area of the neutral zone around the center circle? So to make sure you understand what they're asking, this entire thing is the neutral zone. But they want to know what's not the area of the whole neutral zone, what's the area of the neutral zone not including the circle. So just the area of the neutral zone that does not include the circle. So I want to pause for a second, see if you can figure out what we need to do to figure that out. Okay, so when you're problem solving, it's important to think, well, what do I know and how do I need to get there? So if you look, we could figure out the area of this rectangle pretty easily. So I'll say the area of a rectangle. We know that, or we can find that anyway. I know it's not written, but we can find that. We also know how to find now the area of a circle. What they're wanting us to find, what we're trying to find, is the area of this whole rectangle taking away, meaning subtracting, the circle. So we'll need to find the area of the rectangle and then subtract from that the area of the circle. So big picture, what we're trying to do is find the area of the rectangle and subtract the area of the circle. So the rectangle, we can use length times width or base times height, doesn't matter. So base times height of the rectangle minus pi r squared of the circle. So our base is 54 feet. Our height is 85 feet. And the radius of the circle is given to us right there. It's 15 feet. Now, if you want to plug this all in your calculator all in one line, that should work. As long as you put parentheses where they're needed, and multiplication, the squaring, all that, that should be fine in one line. If you'd rather break it up and do it separately, this times this gives you 4590. Pi times 15 squared gives you 706.86. So if we subtract those from each other, we find out the area I shaded, the area of the neutral zone that does not include the circle, turns out to be 3,883.14 square feet.